This video is about solving quadratics by square roots. Before we can practice solving quadratics with square roots, we need to go over some properties of square roots and learn how to simplify them. So simplest radical form is called that because the root symbol is also called a radical. The number underneath the root symbol is called the radicand. And if the radicand is a perfect square, of course you just simplify it. The square root of 81 is 9, because 81 is a perfect square. If the radicand is not a perfect square, you can apply the product property of square roots, which says you're allowed to rewrite this as the square root of 16 times 5, and then separate this 16 and 5 into two separate radicals. The square root of 16 is, of course, 4, and then we leave the square root of 5 underneath the radical, because it can't be simplified. And so 4 root 5 is the simplest radical form. You can apply the product property of square roots in the other direction, too, and combine this 10 and this 15 to create the square root of 150. And then look if you can simplify 150 in a better way. You can split 150 into the square root of 25 times 6. And, of course, the square root of 25 is 5. We leave the root 6 inside. And so we've simplified this expression into simplest radical form. Another property of square roots is the quotient property, which is similar. It says that if you have the square root of a quotient, you can separate it into the square root of the numerator divided by the square root of the denominator. The square root of 4 is, of course, 2, and the square root of 25 is 5. So if you have two perfect squares, then your answer is just this fraction. If you have a number like the square root of 7 over the square root of 9, simplify what you can simplify, which is the denominator, and leave the square root of 7 on top. It's as simple as it can get. And then in this example here, just remember that sometimes you have to apply the previous rule with this rule. The denominator becomes a 5, but the numerator, we have to simplify the root 24 by breaking it into 4 and 6. And then, of course, the square root of 4 is 2, and that's as simple as this one gets. Now, notice that all of these denominators became rational numbers, 5, 3, and 5, on the denominator of these fractions. If you're going to end up with an example like the square root of 7 over the square root of 5, where you can't simplify the denominator to make it rational, you are expected to do what's called rationalize the number on the bottom. So you're supposed to rationalize your denominators anytime that you're ending your answer with a square root in the bottom. So to rationalize something, you can multiply the fraction on the top and bottom by whatever the number is on the bottom that you're trying to rationalize. So square root 5, we're going to multiply it by another square root 5. The reason we're allowed to do this is because essentially we're just multiplying this fraction by 1. If you do it to the top and bottom, you're not changing the value of the fraction at all. You're just changing the way it looks. The numerator, we can apply our product rule, and 7 times 5 is the square root of 35. And on the denominator, the square root of 5 times the square root of 5 becomes the square root of 25, which is a perfect square and simplifies to just the rational number 5. So now our denominator is a rational number, and it doesn't matter what happened to the numerator, as long as the denominator has become rational. If you have a more complicated thing going on in your denominator, like in this next example, you may have to think a little bit about how can I truly get rid of that square root that's on that 2. Instead of just multiplying by root 2 on the top and bottom this time, we're going to need to multiply by something called the conjugate. The conjugate is identical to the denominator that's there, but with a different sign in the middle. You want to multiply both the numerator and the denominator by the conjugate of the denominator. The reason being, just like a difference of squares, if you FOIL out the bottom here, your middle terms will cancel out, and it's the middle terms that will still have the square root of 2 in them. So I'll show it. The numerator is going to become much more complicated, which is fine. We have to distribute the 3. It's going to become 21 minus 3 root 2. And the denominator has to get FOILed out. At first, it would look like 49 minus 7 root 2 plus 7 root 2, and then minus root 2 times root 2, which is the square root of 4. That simplifies to just plain 2. Notice that the two middle terms in the denominator still have the square root of 2 in them, but they cancel each other out, and that's because we used the conjugate. So the top became uglier, but the denominator became 49 minus 2, which is just 47. You would look to see if you can simplify it in any way. If all of those numbers were divisible by the same thing, you could simplify the fraction, but this one can't be simplified, so we just stop. now we can apply solving quadratic equations with square roots. So the general rule of thumb is that if a quadratic equation is in standard form, which means it's going in the order ax squared plus bx plus c, or basically your x squared term, then your x term, then your constant term, if it has only the a and c terms, then it can be solved using square roots. So if you don't have a b term in your original question, that means the b value is 0, and you can solve it using square roots. So here's an example of one that's missing the b term. So we can solve it using square roots simply by isolating the x. We add 80 to the other side of the equation. We divide both sides by 2. At this step, we're looking for x. We know that x to the second power equals 40. To get rid of the second power on that x, we're going to use the opposite of squared, which is the square root. But you have to put a plus or minus sign in front of the square root sign anytime you're going to use it to solve for x. Do the same thing to the other side of the equation to keep it balanced. And the square cancels out with the square root. The answer is plus or minus the square root of 40. Why does it have to be plus or minus? Because if you think about a number to the second power, that number could be positive or that number could be negative. And either way, it would give you the positive 40, right? So when it said x squared equals 40, there were two possible values for x that would give you 40, a negative one and a positive one. So you need to put a plus or minus in front of your answer. And then, of course, you need to simplify your radical using the rules that we just learned so that your final answer is in simplest radical form. This is actually two answers, just like we practiced with quadratic equations when we were factoring. We were always looking for two answers. Here, one is positive and one is negative, and I'm not going to make you separate them and write it twice, like once with a positive 2 root 10 and once with a negative 2 root 10. You can simply leave the plus or minus sign, and that encompasses both answers. This one looks a little bit different. You can also use square roots to solve if it's in this form, which is called vertex form. And we'll practice it more when we're getting into the graphs of these functions. But if you recognize this form, you have parentheses with a squared outside. This is a typical H and K setup, which we've seen before with other functions like absolute value functions. But if you recognize that it's in this form, you can also use square roots to solve it. My recommendation is do not write the x minus 4 twice and try to FOIL this, because then you'll be putting it into standard form, and then you won't be able to use square roots anymore to solve it. So if it's in this form, leave it in this form when you're trying to solve. It's simpler. You can multiply by 3 to get rid of this fraction that's in front. If you multiply by 3, it simply cancels out the 1/3, and the other side becomes a 33. And at this step, we can use a square root to get rid of this second power, rather than trying to write this thing twice and FOIL it out. So we can just get rid of the squared by putting a plus or minus square root on both sides. Then the left side of the equation becomes x minus 4, and the right side of the equation becomes plus or minus the square root of 33. I can't simplify the square root of 33 at all, so I'm just going to leave it. And of course, now I have to add this 4 to the other side. And the conventional order to write this irrational answer in is the positive 4 first, which is the rational piece, and then plus or minus the irrational piece, and there are the two answers for x right there. Practice one more example like that. We're going to subtract the 3 first. So we want to basically isolate this parentheses. So we're going to subtract the 3 first, then we're going to divide by the 2. That's in front. So now we've isolated the parentheses with the second power on it, and now we can get rid of the second power using plus or minus square root. The left side will say x minus 1. This will simplify into plus or minus 2 root 3. And then we add the 1 to the other side. Remember, the rational part comes first, and the irrational part goes second. And there are the two answers. If you're in a case like this, now this is in standard form, but it has the middle term. So you're not applying square roots as we did in the first example here. But if you recognize what you have on the left side of this equation, it's a perfect square trinomial, which will factor as x plus 4 to the second power. And now you've written it in vertex form, so you can use square roots to solve it. So x plus 4 will equal plus or minus the square root of 27, which simplifies into 3 root 3, and then you move the 4 to the other side, put the rational part first, the irrational part second, and there are the two answers. And then just one extension, so you have a preview of something that's coming, is that not all quadratic equations have real number solutions. The opposite of a real number is something called an imaginary number. We're going to spend quite a bit of time in this chapter looking at imaginary numbers. Well, not looking at them because you can't see them, but we're going to be finding them as solutions. And here's how that's going to look. This equation has an a term and a c term. It does not have the b term. That means I can solve it using a square root. I'm going to subtract the 11. So this will be negative 24. I'm going to divide both sides by 2, so I'm isolating the x squared. And then the last step, of course, to get rid of the second power is to use a plus or minus square root. Now, what we have never seen before is a square root that has a negative number underneath it. It's not possible for anything to multiply by itself to give you a negative 12. Negative 12 cannot have a square root. It is impossible to take the square root of negative anything. There's no way to multiply something by itself to give you a negative. When you end up in this impossible situation, they wanted you to be able to keep going, keep simplifying this answer, even though it's not a real number. We don't want to just quit and say that this thing doesn't have a solution. So what they came up with is simplifying the left side, of course, to just x, and then imagine breaking the right side of this equation into two pieces, the square root of negative 1 times positive 12. Because positive 12 I can deal with. It's the negative 1 that I can't deal with. I cannot have the square root of the negative part of this. Which you can further imagine, got to get that negative underneath, you can further imagine separating it to be this. And now it's just the square root of the negative 1 part that's causing us a problem. So they define the square root of negative 1 to be imaginary. The letter I is used as a placeholder for the square root of negative 1. So the correct way to write this answer, even though it's not a real number, would be to replace the square root of negative 1 with the letter I. And then, of course, if you have a radical that you can simplify, you'll need to do that as well. And the square root of 12 is going to simplify into 2 root 3. The conventional order to write an imaginary answer in would be the 2 followed by the I, and the very last piece is the irrational piece. So this is something called imaginary solutions or complex solutions. And we'll be spending more time later in this chapter looking at complex solutions and complex numbers. And that is all.